Let me welcome you to this lecture. We have now seen how to write the character of a matrix representation for a symmetry operation without even writing the matrix, and only by just looking at the way the vectors reorient or reposition themselves upon performing the symmetry operation. So based on this, we have written a representation of the C2B point group by considering the displacement vectors on all atoms in water molecule as the basis, and the representation that we got for water molecule by considering the C2B point group. The symmetry operations are identity C2 sigma B xz sigma B yz, and when we found a representation by considering the displacement vector on each of the atom as the basis, that we call the gamma 3n, and this was equal to the character of the matrix representation for identity operation was equal to 9, while the character of the matrix representation for C2 operation was equal to -1, and for sigma v xz it was equal to +3, and for sigma v yz it was equal to +1. So this is the representation that we derived by considering the displacement vector on each of the atom in water molecule as the basis. So, and we call this as a representation of the C2B point group. So let us now change the basis and then find a representation of the C2B point group and then see what happens then. So let us now take, instead of displacement vector on each of the atom as the basis, let's now take a displacement vector only on the central atom as the basis. So we take displacement vector, that is x, y, and z on the central atom, that is the oxygen atom, as the basis. You can also tell it to be, say, the p orbitals on the oxygen atom as the basis, because the symmetry of the p orbitals, the lobes on the p orbitals are all oriented towards the Cartesian coordinates along x, y, and z axis, and also the p orbitals have, the lobes on the p orbitals have opposite symmetry. So the positive lobe, we can consider it to be positive axis, while the negative lobe can be considered towards the negative Cartesian coordinate axis. So the representation that we are going to get by considering Cartesian coordinate on the oxygen atom as the basis will be same representation that we are going to get by considering p orbital on the oxygen atom as the basis. We can also get the same representation if we consider the translational modes of the molecule as the basis, because the translational modes are a translation along x, y, or z axis. So the representation that we are going to get here by considering the three-dimensional Cartesian coordinate on the x, y, z along the x, y, z axis on the central matter atom is going to be the same representation that we are going to get when if we consider the oxygen atom of the p orbital on oxygen atom as the basis, or if we consider the translational modes of the molecule as the basis. So let's call it gamma T, this particular representation that we are going to get by using this basis. So we know the matrix representation for such a if we take the gamma translational modes as the basis, the character of the matrix representation for identity operation is going to be equal to 3, because we have only 3 vectors x, y, and z now. So the character of the identity matrix is going to be equal to 3, and it is going to be a 3-dimensional unit matrix for this. So then for the character for C2 operation, you can see that when we use perform C2 is going to be along the z axis. So the z coordinate is not going to change direction, but x and y are going to go to -x and -y, and that is why -1 characters we will get from x and y, while for z we will get +1. So total what we will have, +1 for x, +1 for uh, x goes to minus x, so minus 1 for x, minus 1 for y, and plus 1 for z. So total character of the matrix representation for C2 operation is going to be equal to minus 1 here as well. So then if we do sigma b x z, x and z vectors are not going to change direction, while y will go to minus y, and that is why x will give us plus 1, y will give us minus 1, and z will give us plus 1. So total character of the matrix is going to be equal to plus 1 here. Then sigma b yz, in this case y coordinate is not going to change direction and z coordinate is not going to change direction, while x coordinate will go to minus x when we do sigma v yz, and that is why minus 1 for x, plus 1 for y, and plus 1 for z coordinate, and this is going to be equal to again plus 1. So this is what we get if we have the characters for matrix representation for all the symmetry operations in C2V point group, and this representation that we obtained here, we obtained it by considering the p orbitals on the oxygen atom as the basis, or the three-dimensional Cartesian coordinate only on the central atom as the basis, or we can also say that this we got by taking the translational modes of the molecule as the basis. So this is the representation that we get here. And now what you see that for the same water molecule, we have got two representations for the C2B point group, and these two representations are entirely different from each other. The reason because the basis for obtaining these representations are different. So for the same molecule, we can get different representation of the same point group by considering different bases. So one can also take the vibrational modes as the basis, or the rotational modes of the molecule as the basis, or say for example one can also take the d orbitals as the basis to get different representation of the same molecule in different in the same point group. Say now let us take another molecule which has C2B point group. So let us now take the pyridine molecule as an example. So pyridine molecule also has C2B point group, as you can see here. The C2 axis passes through the top hydrogen atom, this carbon atom, and the nitrogen atom. The C2 axis passes through. There is a sigma b xz, which is the molecular plane of symmetry, and there is a sigma b yz, which bisects the molecule in two halves and contains this hydrogen, this carbon, and this nitrogen atom. So now the number of atoms in this pyridine molecule is equal to 11, because we have 5 carbon, 5 hydrogen, and 1 nitrogen. So total we have 11 atoms in the pyridine molecule. So now if we take displacement vector on each of these 11 atoms as the basis, so we will have total 11 into 3, because on each atom we will have 3 displacement vectors along x, y, and z direction. So we will have total of 33 displacement vectors. In the pyridine molecule, and the matrix representation for identity operation will now be a matrix with 33 rows and 33 columns, or the dimension of the matrix for the identity operation is going to be a 33, and it is going to be a unit matrix of dimension 33. So the character of this matrix, we can easily imagine that this is going to be equal to 33. So gamma 3n for pyridine, the character of identity operation, or matrix representing the identity operation, is going to be equal to 33. Now we can find out the characters of matrix representation for other symmetry operations in C2B point group as well. So when we do C2 operation, we see that all these carbon atoms and the hydrogen atoms on these 4 carbon atoms and hydrogen atoms are going to change position when we do C2 operation, and only this hydrogen atom, this carbon atom and the nitrogen atom over here do not change position when we do C2 operation in this case. So that means these atoms which change positions are going to contribute 0 to the character, and only we have to look at only the atoms whose positions does not change when we perform the C2 operation. And what we will do for only one atom, and then we can add up the characters for all the atoms, because the character essentially for different vectors in all these three atoms are going to change similar way when we do the C2 operation. So let's do it. X, Y, Z coordinates on this hydrogen atom, we will look at how they change for the direction when we do C2 operation. So when we do C2 operation, we see that the Z axis does not change direction, while X goes to minus X and Y goes to minus Y when we do the C2 operation. So X is going to contribute -1, Y is also going to contribute -1 here, and Z is going to contribute +1. So total what we have is equal to -1. Now if this is what we get for the vectors, displacement vectors on the hydrogen atom only. So the character that we get for displacement vectors along the on the hydrogen atom is going to be equal to -1. Then we will have to look at the displacement vectors on this carbon atom, and again the x, y and z axes are going to change that orientation the same way that the Cartesian coordinates in case of the hydrogen atom changes direction, and that is why we will again get character equal to -1 in case of this carbon atom, and similarly in case of the nitrogen atom also the displacement vectors will give total character equal to -1. So the total character of the matrix representation for the C2 operation in case of this pyridine molecule is going to be -1 here and -1. So total it is going to be equal to -3. So then let us find the character of the matrix representation for sigma v x z. In this case, none of the atoms change position, and that is why displacement vector on each of the atom are going to contribute towards the character of the matrix. So we'll do it for one atom, and then we can do sum up for all other atoms, because the change in direction of the displacement vectors are essentially going to be same when we do the sigma v x z operation. So let's find it for this hydrogen atom. When we do sigma v x z, x coordinate is going to contribute +1. Z coordinate is also going to contribute +1 because they do not change direction, but y coordinate is going to contribute to -1 because y goes to -y when we do sigma v x z, and that is why for this hydrogen atom what we will get total is equal to +1, and there are total 11 atoms we know, and in all the cases the x, y and z coordinates are going to change direction the same way that it does in case of this hydrogen atom. So each of the atom are going to contribute +1 to the character, and that is why total character that we will have for this matrix is going to be equal to 11. So then let's go for sigma v yz here, and in case of sigma v yz, again the way atoms in when we do C2 operation, the atom change position. These carbon atoms and the hydrogen atoms which do not fall on the sigma v yz plane are going to change position, and that is why they are not going to contribute towards the character, and only the top hydrogen atom over here, the carbon atom and the nitrogen atom is going to contribute towards the character. And what we will have when we do sigma v yz, again the y coordinate is not going to change direction, while x coordinate is going to go to -x. So x is going to give -1, y will give us +1, and z will give us +1. So total what we have is +1 for the hydrogen atom, for the displacement vectors on the hydrogen atoms contribute total +1 to the character. Similarly, displacement vector on this carbon atom are going to contribute +1 to the character, and this nitrogen atom is also going to contribute +1 to the character. So total what we have is equal to +3. So now we have found out another representation of the C2b point group. Again, That is, by considering the displacement vector on each of the atom in this pyridine molecule. So what it essentially tells us is that we can have infinite number of such representation of the same point group by considering different bases. As we change the basis, the representation of the point group is going to change, and therefore we can have infinite number of representation for the same point group. These representations are of interest to us because we can find many important details about the specific molecules by for which we have found out this representation, and that help us to gain insight into different properties, spectroscopic properties of the molecule or the bonding properties in the molecule. But these representation, as there are infinite number of such representation, they have no fundamental importance as such, and we need to find out representations which have fundamental importance in case of a particular point group. So we will now go and proceed to find out such representations which are of fundamental importance for a particular point group. And before we do this exercise, we will learn about a very special case of matrix multiplication. We will write two matrices and then do their multiplication, and then observe a special case of this matrix multiplication. So let me write these matrices. 1 0 0 1 2 0. So this is the first matrix, and the second matrix is 4 1. So this is the second matrix, and when we multiply this matrix with the second matrix over here, the result that we get is equal to So that is the resulting matrix that we get when we multiply this matrix with this one. This is the matrix that we get as a result. Now, if you look at these matrices carefully, what you will see or what you will observe is that in all of these cases, the non-zero elements appear in blocks along the diagram. That is, you see, this is one block. This is another block in this matrix, and this is the third block in this matrix. So in the second matrix also, the blocks appear along the diagram, and these, what we should also notice is that the fashion in this in which the blocks appear in this case is similar to what in case of the first matrix. Here there is a block. Here this is the first block, which is a 2 by 2 block, we can say. And in this second case, the second block contains only one element, that is 1 by 1 block, and the third block that we have is a 3 by 3 block here. So the same is the case in case of the second matrix, that is the first block is a 2 by 2 block, second block is 1 by 1 block, and the third block is a 3 by 3 block. Now if you look at the product, what you will observe is that the product, in case of the product also, the non-zero elements in the product also appear along blocks in the same fashion. Here also we have a 2 by 2 block, 1 by 1 block, and 3 by 3 block. So this is a very interesting aspect of matrix multiplication, that when you have non-zero elements along the blocks in both of these matrices in the same fashion, in the product matrix also the non-zero elements will appear along blocks in the same fashion. And what is more interesting here is that you can get the product matrix, instead of multiplying the entire matrix here, you can multiply the corresponding blocks to get the resulting block in the product matrix here. So what we can do is that we can multiply the first block here and multiply with the first block here in the second matrix, and that will give us the first block here in the resulting matrix, that is equal to so then it is true also for the second block, as you see that the second block contains only one element. So this is what we get in case of the resulting in the second block in case of the resulting matrix also. We can get it in this way. And what we can do, if you do matrix multiplication for the 3 by 3 block here with the corresponding 3 by 3 block in case of the second matrix, the result will be equal to the 3 by 3 block that is present in case of the resulting matrix. So this will help us to find out or to prove something a very important relation in group theory that we are going to discuss next. We should see this is an observation that we have made essentially in case of matrix multiplication, where the non-zero elements appear along blocks. So individual blocks can be multiplied to get the corresponding block in case of the resulting matrix. So let us now learn how we can find representation of a point group which are of fundamental importance. So let's assume that a set of matrices, say E, A, B, C, representing different symmetry operations, form a representation of a group. Now if we do one similarity transformation on all of these matrices, that is, we can do similarity transformation by using the matrix representation for different symmetry operation. So let us do one similarity transformation, that is, do similarity transformation by D on all of these elements. So then we are going to produce a new set of matrices, that is a E prime here, and when we do similarity transformation on A by again D, we produce another matrix A prime, B dash, B prime here, and similarly we also produce C prime when we do similarity transformation on the matrix C. Now what we can prove is that apart from these set of matrices, that is E, A, B, C, which form a representation of this group, these matrices which are formed upon similarity transformation on the original set of matrices, that is E dash, A dash, B dash, C dash, also form a representation of the same group. That is, what we can do is we can assume that, let us assume that AB, the product of two matrices here, gives us another matrix, that is D. So then, if we do A dash B dash, because we know A dash is equal to D inverse A D, and B dash is equal to D inverse B D. So using associative law of multiplication, which is true in case of mathematical group as well as for matrix representation for different symmetry operations within a mathematical group, that is, we can write D inverse B D. So D inverse will essentially give us identity, and when we multiply identity with A or B, we will get A or B back here. So that is why we can write this equal to AB D. Since we have assumed here that AB is equal to D, so what we can write here is D inverse D D. So when we do similarity transformation on the matrix D, we will get D dash. So what it means that we assume here that AB is equal to D, and that essentially gave us that A dash B dash is equal to D dash. So it tells us that all the products in case of this prime set of matrices or this dash set of matrices that we obtain by doing similarity transformation on the original set of matrices are going to run parallel with the products that we get in case of the parent set of matrices. That means, because when we write A dash B dash is AB is equal to D, we get that A dash B dash is equal to D dash. Similarly, if we assume that AC is equal to, say, X, then what we will get, A dash C dash is going to be X dash. So this is what we mean by saying that the products in case of the prime set of matrices, that is the set of matrices that we obtained by doing similarity transformation on the parent set of matrices, will run parallel to the products that we are going to obtain in case of the parent set of the matrices. So that is why, and that is the reason why we can now say that these set of matrices, that is that we obtain by doing similarity transformation on the parent set of matrices, that is E dash, A dash, B dash, C dash, all the entire set of matrices form a representation of the same group here. So we obtain another set of matrices which again form a representation of the same group. The way we have obtained gamma 3n or say gamma translational, so because they form representation of the same group, that is C2V, we have seen example. So similarly here also, what we have these parent set of matrices and the set of matrices that we obtained by doing similarity transformation on this parent set of matrices, both of these set of matrices form representation of the same group. Now if we assume that these set of matrices that we obtained after doing similarity transformation of the parent set of matrices are essentially matrices which are block factored matrices, that is D dash A D is equal to A dash, D inverse A D is equal to A dash, and A dash is a matrix which is block factored. That is, all the non-zero elements in case of A dash appear along blocks. And if this is true for all the matrices in case of this prime set of matrices, that is, if it is true even for say B, C, and B dash, C dash, and D dash, so that is equal to B dash. In case of B dash also, we can do block factoring in the same fashion that we can do in case of A dash. So what we have is B1 dash, B2 dash, B3 dash, B4 dash, B5 dash. So again, non-zero elements in the matrix B dash also appear in blocks in the same fashion that it appears in case of A dash. So that is true for all the matrices that we, in case of this prime set of matrices, that is C dash, D dash, and as on. So that is, in that case, as we have seen that earlier, that when we have such matrices which can be block factored, then we can get the resulting matrix by multiplying the corresponding blocks in the matrices. That is, since we have assumed that A dash B dash is equal to D dash, or AB is equal to D, then what we can write now is that A1 dash B1 dash will also be equal to D1 dash. That is, when we multiply the corresponding block of matrices in A1 and A dash and B dash, that is A1 dash if we multiply with B1 dash, then we will get D1 dash, that is the corresponding block in case of the resulting matrix in the D dash matrix. So essentially what we can write is that A1, that is A2 dash also, A2 dash, B2 dash will also be equal to D2 dash. And as you can write like this for all the block factors within the this result within these matrices that we obtained by doing similarity transformation, that is A dash or B dash. So essentially what it tells us is that this is a representation of the matrix. This is what of the group. That is what we assumed, and we found out that we proved that the prime set of matrices that we obtained by doing similarity transformation, that is E dash, A dash, B dash, C dash, are also representation of the same group. And now what we have found is that the products in case of these block factored matrices, that these the small blocks within these matrices also run parallel to the products in case of the parent matrices or the matrices that we obtained by doing similarity transformation. And that is why these set of matrices, that is E1 dash, A1 dash, B1 dash, C1 dash, or E2 dash, A2 dash, B2 dash, C2 dash. So similarly E3, E3 dash, A3 dash, B3 dash, and C3 dash. All of these set of matrices which are of reduced dimension now as compared to the dimension of the matrices that we have, the parent matrices or the matrices that we obtain by doing similarity transformation, we see that the dimension of these matrices here, which are small block factored components of the parent matrices essentially. So these also form representation of the same group. Now these set of matrices, that is E, A, B, C, the parent set of matrices, where in which case we can do similarity transformation to produce E dash, A dash, B dash, and C dash, and these can be block factored now into smaller matrices of smaller dimension, actually in the same fashion. So such matrices which can be block factored into smaller matrices of smaller dimension, and these smaller matrices also form representation of the same group. So such matrices we will call reducible representation because we can reduce these matrices into matrices of smaller dimension, and these matrices of the smaller dimension are still representation of the same group. That is why we call these matrices, set of matrices, as reducible representation. Now, if it is not possible to find a similarity transformation to transform a matrix into a matrix which can be essentially block factored into matrices of smaller dimension, in that case, that particular matrix is going to be called irreducible representation, because simply we cannot reduce it any further, or we cannot reduce the dimension of the matrices representing the group into smaller matrices. So, say for example, in case of this set of matrices E1 dash, A1 dash, B1 dash, C1 dash, we are not able to find a similarity transformation to transform these matrices into such matrices which can be further block factorized. So then these matrices will be called irreducible representation of the group. We will see examples of such irreducible representations now. And these irreducible representations, there are only finite number of irreducible representation as compared to the infinite number of reducible representations that are present within a group. And these irreducible representations are of fundamental importance in case of a particular point group. So the difference between reducible representation and irreducible representation is now obvious to us, that reducible representation infinite numbers are present, and we can write different irreducible representation by considering different bases. Also, they are of not fundamental interest and specific to a particular basis or particular molecule. And then what we also have is can be block factor into which are representation of the same group essentially. But irreducible representation, on the contrary, only finite numbers so the number of irreducible representation in a particular point group is a finite number of irreducible representations are only there, and we can find out how many irreducible representations within a point group is there, and cannot be block factored into matrices of smaller dimension. So we will fail to find a similarity transformation that will transform these representations into matrices which can essentially be block factored. So that is why they are called irreducible representation. Now we will see examples of irreducible representation within their present, or we will see how one can block factorize reducible representations into irreducible representations. So let us take once again the C2B point group, and let's write matrix representation for different symmetry operations in C2B point group by considering the three-dimensional Cartesian coordinate as the basis, or if we take the oxygen water molecule, we will get these matrix representations by considering three-dimensional Cartesian coordinate on the central atom as the basis. So for the identity operation, we can write the matrix for C2 along Z direction. This is the matrix representation for sigma V x z This is the matrix representation, and sigma V y z minus 1 0 0 0 1 0 0 0 1. This is the matrix representation. So in this case, in case of the C2B point group, we can block factorize these matrices into matrices of one dimension, that is in this way. So now the character of the corresponding blocks will essentially form one irreducible representation. So C2B, so that is identity C2 sigma V xz sigma V yz, and if we write gamma, that is xyz, that is by taking the three-dimensional Cartesian coordinate on the oxygen atom as the basis for the water molecule in C2B point group, then we get here equal to 3 for the identity operation, the matrix representing identity operation. This is minus 1 and this is plus 1, as well as this is also plus 1. But what we have found now, this is a reducible representation of this C2B point group, because we can reduce the matrices into small blocks of matrices of smaller dimension. And now what we see, this set of matrices here forms one representation of the C2B point group again. So we call it, say, gamma 1 here. So one character of the matrix for identity is 1. For C2 it is minus 1. For sigma B xz it is plus 1. And sigma B yz it is minus 1. So this is a irreducible representation of the C2B point group, because we cannot block factorize these matrices one by one matrices here any further, because we have reached the final limit. So another matrix representation that we have is, if we consider these matrices over here, the second one, so that is plus 1 for identity, minus 1, again minus 1 here, and plus 1 over here. So then we have another one, it is gamma 3. If we consider here 1, 1, 1, and 1. So what we have seen, that in case of this representation that we obtain by considering the three-dimensional Cartesian coordinate on the central atom in water molecule as the basis, and the characters of the matrices for this representation we have found out, but this representation is a reducible representation, that is gamma xyz over here is a reducible representation, and this representation can be reduced into matrices of smaller dimension essentially, and we get the characters of the matrices of the smaller dimension, or these block factored matrices, and these characters essentially form representation which cannot be reduced any further, and that is why these are called the irreducible representation of the C2B point group. Of course, we have not written all the, we are not able to find all the irreducible representation of the C2B point group here so far, because there is a systematic way to find out all the irreducible representation in a particular point group that we will learn in later. But for now, what we see is that this particular reducible representation contains 3 different irreducible representation of the C2B point group. So such reducible representations are essentially formed by one or more, 2 or more irreducible representation of the point group essentially. So we just have the irreducible representations are inside such reducible representations of the same point group. So we will now see another set of matrices and a matrix representation for, say, the C3b point group, and try to identify the irreducible representations in those set of matrices. So let's take the ammonia molecule. We know it belongs to the C3b point group, and the C3b point group has 6 symmetry operations, that is identity, C31, C32, sigma V1, sigma V2, and sigma V. Let's not call them 1, 2, 3. Let's call them sigma V dash, sigma V double dash, sigma V triple dash. And the C3 axis is in this direction, while let's call this sigma V1, sigma V2, and sigma V3. Sorry, sigma V dash, double dash, and triple dash. Dash, double dash, triple dash here. So let's write matrix representation for different symmetry operation in C3b point group by considering 3-dimensional Cartesian coordinate on the central atom, that is nitrogen atom, as the basis. Let's assume this to be x, this to be y, and this to be z. Then we have the matrix representation for identity operation is going to be 3-dimensional unit matrix. For C31, we know it is going to be equal to cos, because 120 degree rotation, cos 120, which is equal to minus half, sin 120, root 3 by 2, 0, minus sin 120, minus root 3 by 2, cos 120, minus half, 0, 0, 0, 1. This is for C31. For C32, it is going to be rotation by 240 degree. So cos 240 is again minus half. Sin 240 is minus root 3 by 2, 0. So then this is going to be plus root 3 by 2, because this is sin 200 minus sin 240, and this is minus half, 0, 0, 0, 1. For sigma v dash, which makes angle 0 with x-axis, what we have is cos 0, which is 1, 0, sin 0, 0, 0, then sin 0 once again, 0, and minus cos 0, so that is minus 1, 0, 0, 0, 1. This is for sigma v dash, and sigma v double dash, that is, it makes 120 degree angle with the x-axis, so that is why we have to take cos 2 beta, which is going to be cos 240 essentially. So cos 240 is equal to minus half, and sin 240 is equal to minus root 3 by 2, 0, minus root 3 by 2, and minus cos 240, that is why it is going to be plus half, 0, 0, 0, 1. Now sigma v triple dash is going to be the angle it makes, this plane makes with the x-axis is 240 degree, and that is why the angle that we have to consider 2 beta is going to be equal to 480 degree, which is 360 plus 120. So essentially it is going to be equal to 120. So cos 120 is again minus half, sin 120 is root 3 by 2, 0, again root 3 by 2, minus cos 120, so that is why plus half, 0, 0, 0, 1. So we have the matrix representation for different symmetry operations in C3b point group that we obtained by considering the 3-dimensional Cartesian coordinate of the nitrogen atom in ammonia molecule as the basis. Now we can see how we can both block factorize these matrices into matrices of smaller dimension, that we can do by considering a 2 by 2 matrix and 1 by 1 matrix in this way. So you can reduce these matrices in this way. So now what we can write that gamma xyz in this case is equal to 3 here. Then this is going to be minus 1 plus 1 0, minus 1 plus 1 0. This is plus 1, this is also plus 1, and this is also plus 1. So then what we have is, we have two representation now, irreducible representation after doing block factoring. In this case, this is going to be equal to 2. The character for this is going to be equal to 2. Then the character for C31 is going to be equal to minus half, minus 1. C32 it is going to be again minus 1. And sigma v dash it is going to be 1 minus 1, that is 0. So 0 and 0 for sigma v double dash and sigma v triple dash as well. The character of the other representation is going to be equal to 1 here for identity, and for C31 it is 1, C32 also it is 1, sigma v dash it is equal to 1, sigma v double dash it is equal to 1, sigma v triple dash also it is equal to 1. So what we see is that the matrix representation that we obtained for for the representation gamma xyz can be reduced into two irreducible representation here. That is, for the one is two-dimensional representation, because we see here that the character of the because the matrices here are two-dimensional. You see that two rows and two columns are there, and that is why the character of the identity matrix here is equal to 2. And by looking at the character of the identity matrix, essentially we can tell the dimensionality of the representation, because the character of the identity operation will be essentially equal to the dimension of the representation. For one-dimensional representation, it is equal to 1, while for two-dimensional representation, it is equal to 2, and for three-dimensional representation, the character is going to be, for the identity operation, is going to be equal to 3. So then we have a two-dimensional representation, and we find the characters of all these two-dimensional, all these symmetry operations for this two-dimensional irreducible representation. Also, we find the characters for, there is a one-dimensional representation, and we find characters for all the one-dimensional representation in this, within this reducible representation. So this is how we can block factorize the matrices. Of course, to find out irreducible representation, we have learned how to find out reducible representation by doing different, using different bases. But we have to learn how we can systematically find out irreducible representation of a particular point group, because this is not the exact procedure to find out irreducible representation. We have, just for the purpose of demonstrating the difference between reducible representation or irreducible representation, or how irreducible representations appear within reducible representations, I have written these matrices and then block factorize them in a way so that we can see the irreducible representations present within the reducible representation. So this essentially brings us to the end of this lecture. We have learned how we can write reducible representation by using different bases for different point groups, and also what we have learned very essentially that these reducible representations are infinite numbers, and one can get different reducible representation for the same point group by considering different bases, or by considering different molecules as well, having the same point group. And also we have learned how about irreducible representations that can be obtained by doing block factoring of reducible representations, and we have seen examples of reducible representation for how we can get reducible representations, or how the reducible representations appear within irreducible representations appear within reducible representation, for in case of two examples here, one for water and one for ammonia molecule. So we'll learn more about irreducible representation, or how one can find out irreducible representation of a point group in the next lecture. So let me thank you for being with me during this lecture.